Introduction to First-Order, First-Degree Differential Equations. Welcome, everyone. Before we dive into the specific method of variable separable that we will be exploring in this lesson, it is essential that we first establish a clear understanding of the specific type of equation we are dealing with. In high school mathematics, our primary focus is on what we call first-order, first-degree differential equations. Now, let's break down what those two terms actually mean. First, when we say first order, we mean that the highest derivative present in the equation is the first derivative, which we denote as di dx. Second, when we say first degree, we are referring to the power of that highest order derivative. In this case, the power of di dx is exactly 1. Generally speaking, an equation of this type can be expressed in the form di dx equals f of x, y. In this expression, f of x, y represents a function that depends on both our independent variable, x, and our dependent variable, y. Understanding this structure is crucial, because as we move to the next slide, we will see how a very specific arrangement of this function allows us to use the separation of variables technique. What are variable separable equations? Think of it this way: we have this function, f of x and y, which we saw on the previous slide. An equation is classified as variable separable if we can take that function and break it down, or factor it, into two completely independent parts. One part must be a function that depends only on x, and the other part must be a function that depends only on y. To be more precise, let's look at the mathematical definition. An equation is variable separable if it can be written in the form di by dx equals g of x multiplied by h of y. In this expression, g of x is a function containing only the variable x, and h of y is a function containing only the variable y. There is no mixing of variables within these two individual functions. If that notation feels a bit abstract, let me explain it in simpler terms. If you are looking at an equation and you realize that you can move all the y terms to one side of the equals sign, pairing them with the die, and move all the x terms to the other side, pairing them with the dx, using only multiplication and division, then you have a variable separable equation. This is the key skill we will need for the identification steps and examples coming up in the next few slides. Now that we have established what a first-order, first-degree differential equation looks like, let's move on to the core concept of today's lesson. What exactly makes an equation variable separable? How to identify variable separable equations. Now that we understand the definition of a variable separable equation from the previous slide, let's move on to the practical side. How do you actually identify one when you see it on an exam? I want you to follow a specific, logical 3-step process to avoid any confusion. Step 1 is to isolate the derivative. Before you do any complex analysis, make sure your equation is neatly organized. You want to ensure the equation is written in the form di by dx equals, or, if you are working with x as the dependent variable, dx by di equals. Essentially, get that derivative all by itself on one side of the equals sign. Step 2 is to analyze the right-hand side. Once the derivative is isolated, look closely at the expression on the right-hand side, which we call f of x, y. This is the most critical part. I want you to ask yourself, can I rewrite this entire expression as a product of two separate brackets, where one bracket contains only x and the other contains only y? Remember, we are looking for multiplication, not addition. Finally, step 3 is to check for addition or subtraction. This is where most students make mistakes. If you see x and y linked together by addition or subtraction, for example, inside a sine function like sine of x plus y, or even just a simple x plus y, and you cannot use algebraic identities to break them apart, then you must conclude that the equation is not variable separable. Keep these steps in mind, because in the next few slides, we are going to look at some specific examples to see this process in action. Illustrative examples. Now that we have covered the theoretical definition of what makes an equation variable separable, let's put that theory into practice with our first algebraic example. Take a look at this equation. di by dx equals x squared times y. Let's perform a step-by-step analysis to see if it fits our criteria. First, we check if the equation is already in the standard form we discussed in the first slide, which is di by dx equals f of x and y in this case. It is. Second, we identify our function. Here, our function, f of x and y, is simply x squared times y. Third, we look closely at the components. We can clearly see that x squared is a function that depends only on the variable x, and y is a function that depends only on the variable y. Fourth, to make it even more obvious, we can rewrite the equation as di by dx equals the quantity x squared, multiplied by the quantity y. This shows the separation clearly. Finally, if we compare this to the mathematical definition we saw on the previous slide, where the equation should look like di by dx equals g of x times h of y, we can conclude that our g of x is x squared, and our h of y is simply y. Because we have successfully factored the right-hand side into two independent functions, our conclusion is that this is indeed a variable separable equation. This simple algebraic separation is exactly what we are looking for before we move on to more complex applications, like the population growth model we will see in the next slide. Illustrative examples continued. Now that we have seen how to identify these equations using a purely algebraic example in the previous slide, let's look at something a bit more practical. In this second example, we'll see a real-world application involving population growth. In the field of biology, we often observe that the rate at which a population grows at any given time, let's call it time t, is directly proportional to the size of the population itself, which we'll represent with the letter p. Mathematically, we express this relationship as the derivative of p with respect to t equals k times p, where k represents a constant growth rate. Let's perform a step-by-step analysis to see if this fits our definition of a variable separable equation. First, we look at the derivative. Here, we have the derivative of p with respect to t. Second, we examine the right-hand side of the equation, which is simply k times p. Third, we need to see if we can split this into two separate functions. Even though k is a constant, we can treat it as a function of t that just happens to never change, so g of t equals k. Then, we have our second part, which is h of p, simply equal to p. Fourth, notice that the equation is already written as a product. The derivative of p with respect to t equals the quantity k, multiplied by the quantity p. Therefore, our conclusion is that this is indeed a variable separable equation. As we will see in the next slide, being able to recognize this structure is crucial, because it allows us to avoid common pitfalls when dealing with more complex expressions. Common mistakes to avoid. Now, before we wrap up with our final summary, I want to pause and highlight some common pitfalls. As you start practicing, you'll find that beginners often misidentify equations, accidentally applying this method where it doesn't belong. So please, be very careful with these three specific scenarios. First, let's look at additive terms. You might see an equation like di by dx equals x plus y. It is very important to note that this equation is not variable separable. Why? Because, as we discussed in our definition earlier, we need to be able to factor the right-hand side into a product. You simply cannot factor x plus y into a product of a function of x and a function of y. Second, watch out for confusion with quotients. This is a tricky one. You might see an equation like di by dx equals x divided by y. Unlike the first example, this equation is variable separable. Remember, division is just multiplication by a reciprocal. We can rewrite this as di by dx equals x times 1 over y. In this case, our x function is just x, and our y function is 1 over y. Since they are multiplied, the separation works perfectly. Finally, be wary of complex arguments. Consider an equation like di by dx equals the natural log of x plus y. In this instance, the equation is not variable separable. The reason is that the x and the y are trapped together inside the argument of the logarithm. Because they are linked by addition inside that function, you cannot use algebra to break them into two separate, independent factors. Keep these distinctions in mind, and you'll be well prepared for our final key takeaways. Key takeaways. First, remember that when we talk about a first-order, first-degree equation, we are specifically looking for equations where the highest derivative present is just I dx, and that derivative is raised only to the power of 1. Second, the defining characteristic of a variable separable equation is that you must be able to express the derivative, I dx, as a product of two distinct parts. A function of x, which we call g of x, multiplied by a function of y, which we call h of y. The core requirement here, as we saw in our examples, is the ability to factor the expression. You are looking for that mathematical split where x and y are no longer tangled together in a single term, but are instead part of separate factors. Finally, keep a sharp eye out for those traps we discussed in the common mistakes slide. If you see x and y linked by addition or subtraction, for instance, inside a sine function or just as a simple sum, and you cannot use algebra to factor them apart, then the method of separation of variables simply cannot be applied. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session to ensure you have a solid foundation before we move on to solving these equations in our next class. Master these identification steps, and you'll be well prepared for the next step, the actual integration process. Great job today!